In what I hope is the final video in this series, I'm going to lay out just an example of how the assembler works. So I'm just trying to do this as a way to help you understand how you would write assembly. We're going to flip it around the other way. We're going to look and say, how does the assembler work? Because if you understand how the assembler works, you then understand how to talk to it and tell it what you want to do. I have here some example code. It won't do much because I don't have the full initialization and I'm missing a few other parts that you need, but I do have a few functions and different things for you to look at. We're going to go through each part of this line by line. So we're going to start with some pseudo operations. The first thing you'll see here is an equate statement saying buff size is equal to 20. This doesn't actually do much yet. Right now, all the assembler has to do is remember that if it ever sees this collection of letters, it needs to replace that with a 20. But so far, we haven't seen that collection, so no big deal. Nothing's happened. Now we're going to go down to an org statement. These are several different ways to write this. RAM start is defined in the header files that NXP or Freescale provides. This is the actual address for our microcontroller, and then these are some commands we won't get into, but this is what you'll see in a default example program. That's actually talking to the linker rather than the assembler. Either way, all of these will have the effect of having something in the direct address space, the space before and including 0x00ff, that space which we can get at very easily. And here I've got a little variable called crit. It's just 1 byte long. So every instance of crit, we're going to replace that with hex 60. Now, why is that? Because we started here and it's the first thing that was defined. The next thing we do is we have an org statement, so we're going to move out to the areas of RAM that aren't directly addressable. They can be still reached by the extended addressing mode, but they'll be a little slower to get to. And I've declared here two variables, buffer and low, meaning low priority. Now, buffer is of size, a number of bytes, buff size. Now, at this point, the assembler has to say, wait, I don't know what buff size is. Wait, no, actually I do. Up here, they said if I saw buff size, I'd see 20. So the very first thing that the assembler does is say, nope, that's 20. Okay, I can define 20 bytes. I'm quite comfortable defining 20 bytes. So now buff is 0, 100, and we move on to the next line. Low is just supposed to be 1 byte, but it's after buffer. So if buff size is 20, then there were 20 elements. 20 in hex, well, we need a 16, and then we need 4. If it was size 1, we'd be at 1. If it was size 2, we'd be at 2. So we need to be at 20. And so low is now there. But you can see how, since you personally don't have to calculate this, it's useful to have the assembler do that for you. Now let's look at this constant and lookup table definition section. This is different from the EQUs for reasons we'll get into. First thing we have is we have an org statement that goes to hex E000 or ROM start, which is defined in the header from Freescale. And we define a label lookup, and then we're going to define some constants. Specifically, we're going to define a rather long string with 35 characters. I counted that in Word, by the way, not by hand. Then I'm going to suggest that we define a label called lookup end. We're not going to use lookup end directly, but we will use the difference between lookup end and lookup in order to programmatically determine how many characters are in this string, so that if I then update this string, I can use the difference between these two as a constant to do checks to see if we've gone past the end of the string. You could also null terminate the string with another byte. This is just a different technique to show you. Now that does make the label lookup BE000. It also makes the lookup end BE02 is 32 and then 3 is 35. But unlike up here with the EQU statement, now we have a bunch of stuff that actually happens. So T is some value in ASCII, and the first byte E000 will get the value of T in ASCII, and H is some value in ASCII, and that'll live in E001, and I is another value, that'll live in 002, and so on and so forth until all up to and including E022 are filled with values. Okay, so that's the easy bit. Now we're going to scroll down to the start of the program. Now I've got these big comment blocks here just to show the programmer who comes after me a little bit of help in terms of getting oriented with what I'm doing. I find them helpful. You don't have to use them necessarily. First note is that at this point when we're defining a label in its start, we need to know where we were. Oh, we were just at E023, which is also going to happen to be labeled lookup end. But that doesn't bother us. We can have two labels for the same spot in memory. So this right here, we're currently at E023. Initialization code, typically there's lots of initialization code. We do all sorts of things, select our clock speed, turn on ports and that sort of stuff. I'm going to skip that. I'm just going to assume that you can write initialization code at this point. So as far as this main loop, this is going to be at some other address. Let's just pretend for now that that's E100 because that's easy. And I've omitted some code here. There's some random code. So then let's say there's hex 100 bytes of code. So now here we're down at E200. And then this is a little segment that grabs crit from the SCI, tests to see if it's less than the buff size, and stores it into the crit variable. So the first step is we're going to load A from the SCID. So now the assembler has to figure out, what is load A? Well, first it needs to figure out what is SCID. Turns out SCID, which ought to be defined in your header file, is hex 27. Load A has many different forms. If you look at your manual on page 100, you'd see that there are at least 8 different addressing modes. However, this expression, load A, is followed by a number. It is not followed by a number sign, so we're not using immediate addressing. It's followed by a 16-bit value. But that 16-bit value starts with 00, so we can omit the 00 and use direct addressing mode. So this then, in memory, is going to become B627. 2 bytes of memory. This is the operation load A direct, and this is the direct address that would be used. Not too bad. Now, we're going to do a comparison operation to buff size. Oh, fun fact, I have an error in my program. We're going to do a comparison to buff size, but I want to compare to the number buff size, don't I? I don't want to compare to spot 20 in memory. I want to compare to the number buff size. So the compare operator, again, has about 8 different addressing forms. This is the immediate form. We're going to compare to a number. That number, by the way, we know that number is 20, decimal 20. So we're going to compare to that. The compare immediate form is A1, and then we're going to compare to 20. Now that's 14 in hex. So again, compare immediate and then the immediate value. The next instruction is BLO, which stands for branch lower, branch if lower. If it's lower, we're going to branch past this subroutine. This is one of those cases where we're going to run this subroutine if it's equal to or greater than the buff size. So we want it to be strictly less than because the buffer goes from the start to the buff size -1. We want this value we read from the SCID to be less than that. BLO is a command. It only has one addressing mode, so the assembler doesn't have to work very hard. It's 25 and then a relative offset. We haven't talked about relative offsetting mode yet, but the idea is where do I have to move from where the program counter would be at the end of reading me. It's only an 8-bit value, so it's the case that once we figure out where or how long the next instruction is, then we'll know how far we need to go. We know we're going to point here at the end of this instruction because we always point at the beginning of the next instruction at the end of reading our current value. And I happen to know the jump subroutine is going to be 3 bytes long. So this is going to be just a 3 to say, if this is true, go ahead and add 3 to the program counter to jump past. Jump subroutine has 5 different addressing modes. The assembler knows we're going to jump to a subroutine, just doesn't know which one or how to write it yet because it doesn't know which mode. Most of them are indexed modes, and we're not using index because there's no $X. We either get an 8-bit value or a 16-bit value. Now, I don't know yet where that's going to land in memory, so allow me to put some X's here. But I do know that the subroutine is in program memory. So I'm going to assume, since it's greater than E000, that we need 16 bits. So then if we're in extended mode, we're talking about the command, the opcode CC. Now might be a good time to mention that this does what's called 2-pass assembly, because sometimes we run into things like labels that we don't quite understand what they are yet, right? Handle bound error hasn't been defined, and so it's hard to know how far we have to go. So it's actually going to do a first pass where it does as much as it can, and then it'll tie in remaining labels and things later. So it'll figure out this XX, and it might even change its mind. It might go to direct addressing if it turns out the handle bound error is somewhere in early RAM. But we've jumped past there. The next command is store A, and it's in the location crit. So store A has 7 different forms. There's no real clues to tell us which one, except there's no X's or stack pointers, so it's either direct or extended. Turns out there's no immediate addressing mode because that doesn't make sense. You wouldn't store A into a number. There's just store A to a place. And this crit, this thing here, it has to ask what that is. That crit is back around hex 60 if it's in the direct addressing area. So we can use direct addressing mode. So that becomes B760. Remember, we've been talking about how to access the ith element of an array. This array is named buffer, which typically you'd probably be using a circular buffer or something similar, but here's just a quick example of how we might do that. So we're going to clear the H register because we're going to pay a little more attention this time, and we're going to note that if we're going to use the HX register as an offset, as we've talked about in the last couple of videos, that we really want to make sure that that offset is the same value as crit. Now, crit is an 8-bit value. The HX register is a 16-bit register, so we have to clear H first. We want that to be 0. Clear H, perhaps not surprisingly, only has one form, and that form is given by the command 8c. You'll notice in your book that it says INH. That stands for inherent. As is perhaps obvious, you don't need an address for clear H. You know that you're clearing the H register. There's only one H register. There's no need for anything else. Inherent means the command inherently tells you what spot in memory you're going to touch or what spot on the microprocessor you're going to touch. Clear H, clear A, these sorts of things are inherent. Increment A, increment X would similarly be inherently addressed. Okay, then we're going to load X with crit. Load X has a lot of forms. We don't have X's or SPs. We also don't have an immediate sign. So we're in either an 8 or a 16-bit mode, either direct or extended. And crit, remember, was in that direct addressing space. So the first thing it'll do is say, okay, that's 0060, and then it'll say, oh, that's less than hex 100, so we can use the direct mode again. So the direct mode of load X is BE followed by the address you want to load, which is 60. And the next thing we want to do is we want to load A from X with an offset. So now we're going to look at that load A command, lots of forms again. Which one is it? Well, it's not immediate, it's not direct or extended because we have this X here. It's also not just IX because that wouldn't have something written here. This buffer number, that happens to be hex 100. That's not a good 8-bit value, it's a good 16-bit value. So then we know we're in extended addressing mode, and that command is C6 followed by the extended address 0100. There's my hex 100 right there. That's the location of buff. Okay, and then we have some more code down here. And below that, I just have one statement. It says, branch always to the main loop. I've got a comment here I'll explain in a second. Now, in order to get back to the main loop, we're trying to get back to E100. We know that we were at E200 here, so 200, 201, 202, 203, 2100. So there's also some stuff here. I don't know how long that other code is. If we assume that this here is at E250, branch always is 20, so it's a big break. It's 20 followed by a relative address. Now that relative address is a signed 8-bit value. You can branch forward or backwards. But a signed 8-bit value cannot take us back 150 hex spots. We can't do it. So instead of a branch instruction, we're going to use jump instruction. Now, your assembler actually would come here and it would throw an error. It would say, I can't get using 1 byte. I can't get back to there. So you're going to have to put a jump statement instead. The only difference between a branch always and a jump is that jumps offer the ability to do extended addresses, whereas all branch commands use relative. They can only go back 120 some odd bytes, and they can only go forward 120 some odd bytes. So instead of branch always, they're going to have to do a JMP main loop instruction. JMP has a few modes. We're not going to do any of the index modes. We can't do an 8-bit mode because we're not jumping to something below hex 100. So we're going to have a jump main loop. Main loop is E100. And that we're going to have to translate into, instead of 20 RR, CC E100.